Hello, good afternoon, everyone. I am Provit Maiti. S- Hello, good afternoon, everyone. I am Provit Maiti. Today, I am taking the live session of today's problem solving classes. So, the course name of this course was Symmetry, Stereochemistry, and Application, and instructor was Professor Angshuman Roy Choudhury. I am doing that problem solving classes of this course. So, today's So in these classes, we are mainly concentrated on the problem solving on the conformation of a molecule and which conformation is stable or not. So for the conformation of any molecule, so there will be two conformation. Like one is will be your laser pointer. So the conformation mainly two types. One is your eclipsed conformation. Eclipsed conformation means where your the dihedral angle between the first carbon in this side and the behind that carbon are the angle between these two carbon is generally 0 degree. A staggered conformation means when it the dihedral angle between that carbon in the conformation in the Newman projection will be 180 degree, that will be staggered. So there will be staggered like anti-staggered and anything, so that depend on how this conformation, like how this conformation will be like. So eclipse conformation where the dihedral angle will be 0, and staggered where the dihedral angle will be maximum 180 degree. So the what is the dihedral angle or torsional angle? If the carbon is like that, A, and the bond angle between these two carbon, this one will be bond angle, and the dihedral angle will be that in this carbon and behind this carbon, what will be the, if this substitution are present, so what will be the angle between these two? So this will be our dihedral angle. So dihedral angle, if these two carbon, this B and C, this carbon and that behind carbon B and C, and the substituent are placed like A and D. So what will be the angle between this A and D? So this angle will be our dihedral angle. So if the dihedral angle is 0, that will be eclipsed conformation. If this will be greater than 0, then will be staggered conformation. So further, so if the conformation will be eclipsed or staggered, what conformation will be stable? So before the stable conformation, we have to know that what are the reason for the conformation will be destabilized. The destabilization region are, one is the steric region. So if these two methyl is in the same plane, so there will be steric interaction between these two. So for this steric interaction, the these conformations are not favorable. So these are not stable conformations. So the destabilization are arise due to the steric region, one thing, and next thing will be torsion. Torsion is between this bond and this bond. So they have that electron cloud is here. If these electron clouds are repel each other, so they are torsionally destabilize. And next one is the angle for sp3, like we have that 109 degree, but if the conformation will be any other conformation is like that, so if the angle is beyond this or below this the normal angle of the sp3 or sp2 carbon, so this also destabilize our conformation. So between these two conformation, like this an example of um, 1,2-dimethyl butane molecule. So in this example, we have seen that there will be one conformation is anti, where the two methyl group are far apart from one one to another. So in that conformation, two methyl is far apart to one each another. So there will be no steric interaction. So this conformation should be more stable. So anti means this methyl and this methyl, the dihedral angle between these two will be 180 degree. In the next example, this when this dihedral angle, so first we'll start from here. When the dihedral angle will be 0, these two methyl are in the same, so 0 degree dihedral, so these are like eclipsed conformation, or we can see in conformation. In this conformation two methyl are same, so dihedral angle is 0, so this eclipsed conformation, these are less stable one. This one is the Gaussian conformation. When so we have fixed this CH3 and rotate the first carbon like 60 degree, uh, that clockwise rotation. So after 60 degree rotation, this methyl comes here. So this methyl comes here means, so this conformation we call that Gaussian conformation. So the angle between this methyl and this methyl, the dihedral angle will be 60 degree. Next one is the methyl is going here, there is another 60 degree rotation, so total 120 degree rotation. So these are like an eclipsed conformation, but this conformation is stable more than this, because there will be steric interaction between methyl and hydrogen, and here will be steric interaction between two bulk air group, two methyl group. So this one, and that then the anti-conformation. In this anti-conformation, so there another 60 degree rotation of this carbon. So this two methyl group are far apart from each other, and there will be no interaction between this hydrogen also in between this angle. So this one the stable anti-conformation of this molecule. So the conformation where the dihedral angle between these two methyl group is 180 degree. So what is the, so I have already tell the stabilization destabilization conformation is mainly due to the steric interaction and torsional, that is the dihedral angle between this, dihedral angle between this, and in the torsional strain, that is the two electron cloud is in the same position, so there will be repulsion between each other, so they destabilize our conformation. So for these cases, so we have started, like for that molecule we have seen this molecule, and we have given that Newman projection of that molecule. So Newman projection will be like this. So when the, so first we started, this two methyl group are in the same dihedral angle, that is the dihedral angle between these two methyl are 0 degree. Then it's that the this carbon, that behind carbon is rotated 60 degree for each cases. So when 60 degree rotation, so these are will be our Cauchy conformation. So this one will be stable than this conformation, because these two methyl are more sterically bulky group, more sterically crowded and less sterically crowded. Then the next 60 degree rotation, that is the total 120 degree rotation, these are also eclipsed conformation. In eclipsed conformation, these are more stable than that. So energy is highest means that the less stable, energy is lowest means more stable. So between these two conformations, so this conformation is stable. So after another 20 degree rotation, that is 180 degree rotation. So in this 180 degree rotation, these two methyl are far apart from each other, so there will be no interaction between this. So these are more stable conformation, that is the anti-conformation will be more stable one. Then another 60 degree rotation to 40 degrees, so these are also eclipsed conformation. So this eclipsed conformation are similar like these two, so these two are similarly stabilized. Again 60 degree rotation, that is the 300 degree rotation. So 300 degree rotation, again the Gauss conformation coming. So this conformation are similar stabilized like this. Then again 360 degree rotate, and again 60 degree rotation, that is the total 360 degree rotation, the original molecule is coming. So these are same like. So apart from this destabilizer, so for this molecule we have seen that the anti-periplanar conformation, that is staggered anti-conformation, is our most stable conformation when the two methyl group are far apart from each other. So if there will be so the stabilized conformation will be our anti-conformation. So if there will be any possibility of hydrogen bonding, like for hydrogen bonding happens, so there will be one electronegative group attached with the hydrogen bond, and there will be another electronegative group, like there will be two OH, like in this position, like OH and OH. So what will happen? So that time this hydrogen, if I take my pen, so screen, so point. If I replace this methyl, like replace this methyl by OH, so what will happen? So in these cases, so this OH, and there are also one OH. So what will happen? So this will be hydrogen bonded along like that. So if this hydrogen bonding happens like that, so then this hydrogen bonding make this conformation more stable. So that cases this our gauge conformation will be stable, because in this anti-conformation if we place OH here, so in this anti-conformation the OH is far apart, so there will be no chance of hydrogen bonding, because the hydrogen bonding needs a minimum distance. So for that cases, um, so for that gauge conformation will be more stable. That anti-1 would be not stabilized as compared to gauge. So for these cases, the hydrogen bonding, gauge conference will be more stable. And if there will be electronegative element will be attached, like any, so if any chlorine or bromine will be attached, like electronegative group chlorine is attached, and there will be hydrogen, so there will be some chance of sigma to pi star interaction, like, so for sigma to sigma star to sigma electron donation that will happen, so that will be sigma to sigma star electron donation will happen only that gauge conformation. For that cases, so there are conformation will be gauge conformation will be stable. So what will be the destabilization, and how much destability will happen when that two hydrogen is each other, like these cases. So for that cases, the torsional strain will be around, our molecule will be destabilized like around 4 kilojoule per mole. If there will be methyl and hydrogen is present, so then it will be 6 kilojoule per mole. If there will be 2 methyl with the 2 bulkier group, so that will be 11 kilojoule per mole. And if this 2 methyl in that Gauss conformation like this and this, so like that Gauss conformation, so then that will be 3.8 kilojoule per mole. So next we go to the problem solving. So for these classes we have problem solve, like we have to draw that, we have to draw the energy profile diagram of given molecule of CC bond. So this two bond we have drawing the that uh, draw that molecular diagram conformation. So this molecule I have written here. So this carbon and that carbon. So this two carbon will be fixed like this, and behind there will be another carbon. So I have seen that molecule like from this direction. So if I seen this molecule like in that direction, so then what will happen? In our molecule, NH2 will be above. So our NH2 will be above, and two hydrogen will be here. And this will be OH, it will be lower, and two hydrogen is here. So for that cases, we have to draw the energy profile diagram. So similar like that earlier cases, we have to draw all that possible conformation, then energy profile diagram. And I also tell that for if that will be some hydrogen bonding happens between two molecules, like this there will be NH2 group and there will be OH group. So we are first we'll draw like when that angle between this NH2 and OH 0 degree. So that this will be energy. So when that so that will be the cases. So this OH will be behind this here. Like we could draw like that. So for that cases, NH2 is this. So diagonal between angle between this NH2 and OH is 0 degree. So this is 0 degree. I've written 0. This one is 60, 120, 80, three 300. Next one will be 360. So when the torsion diagonal angle or torsional angle will be 0 degree, so this one will be less stable conformation like that. So again, when the diagonal angle will be 60 degrees, so I have told that when the diagonal angle will be 60 degrees, so in that cases, in the respective position there will be hydrogen like that. So you can write in there. So I have only seen that NH2 and OH position. So when the 60 degrees, so this will be our position. So for that cases, what will happen? So this will be 60 degree, but this in these cases, this one will stabilize that, and further stabilization happen due to that hydrogen bonding. So this OH hydrogen bonded through this nitrogen, or this hydrogen is bonded to oxygen like that. So for that cases, this will be more stable conformation. So like this energy will be like that. Then another 60-degree rotation. So then what will happen? So this NH2 is fixed, and that then the ROH will be come here. So what will happen? So this are similar like this conformation, but is stable, little stable than that conformation, but is not much stable like this conformation. So this energy will be somewhere here. So again that 180 degree means there will be NH2 and OH are going to be far apart. So this conformation also stable, but not stable as like that Gaussian conformation. So this energy is somewhere higher than that Gaussian. because the anti-conformation will be stable, but that not stable as like that Gauge conformation, because in that Gauge conformation there will be external hydrogen bonding is there. Similarly, if we rotate this OH like this, so similar thing happens like 120 degree, like that, the energy. If we rotate this carbon 300 degree, 300 degree means this will be again Gauge conformation. So the Gauge conformation will be stable, more stable. Again 360 degrees, so this one will be here. So our energy profile will diagram will be like that. So like that will be our energy profile diagram. So this conformation and this Gauge conformation is more stable. This one is anti-conformation. These are eclipsed conformation, least stable, and these are also eclipsed, but this for these two cases, so that NH2 and OH is far apart. So this conformation is literally uh, less stable than the anti-conformation and more stable than that our uh, original eclipse conformation, where the dihedral angle is 0 degree. So our most stable conformation will be like this conformation and this conformation, like that Gauge conformation one. So we have to draw that all the Newman projection of this. Then we have to draw that energy profile diagram, and then we have to tell that which conformation is stable. So so again the cases. So before the starting up to this example, so we have shown some similar example like when the methyl group is present here in that equatorial or axial position, what will happen. So like this, if you draw that molecule, so one methyl group is above, one methyl group is below. So if I draw like that, one methyl group is above and one methyl group is below. And if we flip that conformation, so after flipping, what will happen? So after flipping, so this methyl which goes axial. So this methyl goes axial. Also this methyl goes axial. So when these two methyl groups are going axial, so then what will happen? So these two methyl groups is far apart from each other, and so there will be maximum steric indents between these two, and here will be minimum steric indent and some steric indents like little hydrogen molecule. So for these cases, this conformation is more stable. So our conformation will be when these two methyl group is far apart, like that axial conformation. So this will be more stable one. So similar for these cases when these two bromide is bulkier group. So this between these two, so this conformation will be more stable. And if we draw like that, that conformation, like in this conformation, what will happen? So if I draw like similar, and for that conformation, so for this conformation, so this methyl 2 group will be far apart like this. So our one methyl group or bromide group will be here, group will be here. So just to replace this methyl by bromide, so you have to draw like that, and we have to So this conformation will be like that. So these two Br group is far apart, so this will be more stable conformation. And for these cases, what will happen? For these cases, so this Br is coming like this, like that. So like that, similar like this. So for that cases, so our this conformation will be the less stable because this bulk bromide group has only far apart from 60-degree angle. So this will be our less stable conformation. So we have to draw like this Newman projection and tell that when this will be bromide will be 60-degree between the angle. So this will be bulkier bromide group are sterically crowded. So this will be our least stable conformation, and this bromide group when the far apart, that is the axial position. So this stable conformation will be more stable one. So another example when the tert-butyl group are position here. So tert-butyl groups, so our axial hydrogen will be like that. So tert-butyl also a very bulky group. So there will be sterically crowding like this, sterically crowding, and there will be hydrogen. The steric crowding between these two. So what will happen? So this conformation will be less stable. But when this tert-butyl is in the equatorial carbon, so what will happen? So there will be no much steric hindrance is present here. So for that cases, so this conformation will be our more stable conformation. So also we can draw that Newman projection of this conformation, and after drawing that we have to tell that this when these two hydrogen are when the tert-butyl group is in the axial position. So this one is axial position, this one is equatorial position. So when these are in axial position, there will be steric crowding between hydrogen and tert-butyl group. So this conformation will be less stable. And when this an equatorial position, so there will be not much steric hindrance between this hydrogen and tert-butyl group. So this conformation will be more stable as compared to this. So again, next example, we have to tell that in between this one is our chair conformation, this one is our boat conformation. So we have to tell which conformation is more stable, chair or boat conformation. So if I show that if so there will be hydrogen is placing a chair for boat conformation. So the our boat conformation will be like that. This one is boat conformation. I have draw. So this boat conformation, this hydrogen will be like this. That steric hindrance between these two hydrogen. And if there will be in chair conformation, so the steric crowding, so these two hydrogen is far apart as compared to the boat. So these two hydrogens far apart, so this conformation is more stable one as compared to boat conformation. So for normal cases between chair and boat conformation, the chair conformation is more stable one. So this conformation is more stable, and the boat compression would be the less stable. Now go to the next example. So I have tell something about that chiral molecule. So what before the starting the chiral molecule, so how we identify the chiral molecule? So identification of chiral molecule first developed by, so I have taken pointer. So chiral substance means who rotate or plane polarized light. The chiral substance will be that one who rotate or plane polarized. If the plane polarized light is, if a molecule rotate our light positive or negative direction, so then we can tell this molecule is a chiral molecule. So the chiral substance of rotate of plane polarized was first discovered by Jean Baptiste Jean Biot, like 1812. So how is this? Oh, when we flash a light source, and if our molecule, if our light after going here, if a light is passing from that molecule, if this light is rotate like this direction, so from this direction to this direction, so that will be small rotation to the right. If the rotation will be left direction, so like our uh, light will be rotate, so this molecule is our chiral molecule. And when this rotation, the positive rotation and negative rotation are same, so what will happen? So total net rotation will be 0. So then our molecule will be uh, enantiomer. Enantiomer means when that two isomers, that R isomer, that is R isomer, which is rotate the plane polarized negative direction, and S isomer, which rotate the plane polarized in right direction, each like that positive direction. So uh, if all are similar, so then our molecule will be enantiomer. And so for a chiral axis, we have to given that some isomer will be more than one conformation, like if R will be excess or S will be excess, so then that will be uh, enantiomeric excess. Similar the chirality, so this one the chiral molecule where the chirality is because of the in this point there will be four different substituents present in that carbon. So this one called that point chirality. And for that molecule, if I show this molecule, so this biphenyl group, so due to steric hindrance between this NO2 and this COO, so these are not in the same plane. So this one in the above plane, like my side, and this plane. So this is, if I consider this is in the plane, and this one is the above plane, and this is the below plane. So like that, so there will be, this one is the axial chirality. So this axial chirality was first developed by George Christie and James Skinner. The discovery of atrobisomer. So this type of axial chirality is called atrobisomer. This atrobisomer, its properties are first discovered by Richard Kuhn, 1933. So if these two molecule, so if you show this molecule by the carbon, hydrogen, fluorine, chlorine, bromide, and in that carbon, chlorine, bromine, hydrogen, fluoride. So all the four substituents are not in that same plane. So if we see that molecule, so what we'll see? So these are looking similar. These two molecules are looking similar. But if we when we placed this molecule into that molecule, so what will happen? So this Br, this side, like our hand, if our left hand and right hand, if we place two hand like similar, they never get superimposed like one after another. So if I place this molecule here, so there will be never superimposed. So for chiral molecule, we have the non-superimposable mirror image. So our mirror image will be non-superimposable, not placed to one each another. Like similar to that molecule, the axial chirality above. So for this molecule, if I place this molecule, so this the bulkhead group this side, this bulkhead group our side. So if I place that molecule, they are not superimposed mirror image, so they are point chiral and they are axial chiral. So atropisomer is comes the Greek letter. So sorry for the interruption. So I'm going to start. So I tell that the point chirality above. So I take the point chirality. Point chirality means the in between point there will be four another substance in a carbon atom. So this one is the point chirality. So for that point chirality, the molecule will be chiral when they give the super non-superimposable mirror image, like our left hand and right hand. Similar, the for the another cases the axial chirality. Axial chirality is arises due to the when also there will be non-superimposable mirror image, but there will be no point is there. So there will be due to the axial chirality is above. Due to the steric region. So atropisomers is the so that axial chirality is called that atropisomer. The atropisomer is coming the word from the Greek word atrops, that is that without turn. So there will be some steric region. So there's for that region, so the molecule are not rotate freely. And axial chirality arises due to the presence of bulky group along a single bond. In that single bond, there will be placed a bulkier group, and due to this bulkier group, these are not in the same plane. So this will be our atropisomer. So before this chirality, so I have what this chiral molecule are applied. So this chiral molecule are applied mostly maximum in drug application. So in the drug application, we saw that the application of chiral molecule as a drug like 2004 and 2006, this blue region, that blue bar, the single blue bar percentage of shown are some red bar that are approved over the years. Percentage shown racemate red bars including diastereomer, single enantiomer is blue bar. So if you told that that chiral molecule, the maximum chiral molecule are used as drug application if there will be um, that blue bars means that will be single enantiomer. So for that chiral molecule we have if there will be single enantiomer, so that as used as a drug in most of the cases. So there will be some incident or uh, uh, in that in our history like 1952. So what will happen that time, there will be some disaster you already know, like thalidomide disaster. So that thalidomide disaster happens in 1952, mainly in after the World War. So what will happen in that 1952? So there will be one drug like this thalidomide drug is so the thalidomide drug. So this thalidomide drug are mainly used for that morning sickness disease. So morning sickness disease is mainly used for that pregnant women who are used this drug. So after taking this discovery of drug, so this will be nice, nicely treated with the human, and that will be also men will be men are profitable from this drug. But after some incidents, after discovery of the drug, after 2 or 3 years, what will happen? So there will be some cases. So like this. So after that, baby, after borning the baby, so what will happen? So there will be some disability. So like if you show this little girl picture, there will be this hand are not missing. So the growth of this our body part are not evenly happened. So what will happen in the drug? So maybe this drug some tetrazonic, that is the toxic effect in our body. So before the drug will be coming into the market, so what will happen? So this if we show that molecule, this thalidomide molecule, that will be one thalidomide ring, six member, and glutalamide ring is here. So here there will be axial chirality. So this molecule are also chiral molecule. So these are R isomer and these are S isomer. And our also body is mainly in our body is mainly presence of amino acid. So amino acid also are chiral molecules. So the chiral molecules function in our body. So what will happen that R isomer, that mm, is the drug on the R isomer, when the in the drug the R isomer is present, so that will be our in our health, that will be profitable. But when in that S isomer, so that will be tetrazonic, that is the toxic effect. So due to what will happen in our body, this R convert to S isomer. That rapid conversion of R to S isomer is happened in our body pH. So what happens this when we take our drug, so this R converted to S isomer. So after converting this S isomer, so the our body take this drug, and our body toxicity of this drug will affect our body, and so for that reason we have they born that disabilities of baby. So for that chiral molecule, we have to also know that so we have to know that so I have to just giving an example that how was important of our chiral molecule to know that which molecule is chiral and which molecule are not chiral, and how this chiral molecule affect in our body. So it's only just change in that R to S isomer. So our body will affect differently. One the cases, so these are help to our body. In another cases, these are not helping. These are mainly toxic for our body. So to know the chirality, so this will be very important. So now we have to find that if some molecule is chiral or not chiral. So for in these cases, so if we classify this molecule as a chiral or not chiral, so first we have to know if this molecule for chiral molecule, we have to know that our molecule should be non-superimposable mirror image. If I placed one mirror is here, then what will happen? And if I draw that molecule after the mirror, so this will be like that. CL. So if we place this molecule is here, so like similar is placed, that molecule is similar to here. So this mirror image are superimposable to each other. So this mirror image are superimposable each other. So these are not bichiral molecule. So this molecule are not chiral. So this will be our achiral molecule. So this will be our achiral molecule. So chiral molecule, we have to know that for that chiral molecule we have to get that non-superimposable mirror, similar to this compound like 1,2-diamonocyclohexane. So for that cases 2 bromo are in that above. So if we have a plus one plane is here, like so these are opposite to each other, same thing. So this molecule also we have called meso compound. So this meso compound, if any molecule, if there will be one plane, one sigma plane or like that, passing to each other, and we get same molecule to here. So these are called meso compound. So this meso compound are not chiral, a chiral molecule. And if the cases, if the another cases when that bromide is above and one bromide is down. So for that cases, and if we place one plane is here, sigma plane or mirror. So what will happen in that cases? So one bromide is above. So on a mirror, so this bromide should be above is here. So but this bromide not above, this bromide is down. So these are not superimposed. If we also placed one mirror like that, and if we draw that molecule, so this bromide is up and this bromide is down. So like I've dotted. So this all were dotted. So this bromide is down. So if we place this molecule here, so these are not superimposable. So they are giving that chiral molecule. So this molecule are chiral. So these two are chiral molecule, but these are not chiral. This molecule also we can call that meso compound. So for our cases, so this molecule are not chiral. So this one will be our achiral molecule. Similar, for this molecule, we have to find out this molecule is chiral or not. So we have first draw the mirror image. So if we draw that mirror image, so what will happen? So this chloride will be here, and this one the dotted one, the chloride is below. So for that cases, if we place this molecule, oh sorry, I've draw. So this will be our dotted, and this will be our the above. For this will be the above. So for that cases, what will happen? So these are not superimposable to each other. So these molecules would be chiral molecule. So when these two chloride in the trans conformation, so trans means that one is above and one is down. So trans conformation, so then that molecule will be chiral compound, and when they are in that cis conformation, so they would be the achiral compound. So similarly, the next example one. So in that next example, we have to also tell that which molecule is this molecule is chiral or not. So if I saw that molecule and after seeing that molecule, like similar to this molecule, I have given example. So you have to draw its conformation. So I have draw that conformation. There will be CH3 like it's here, and I have seen from this direction. And so if I seen from this direction, so our chloride will be which side? Right hand side. So here our chloride will be placed right hand. Oh sorry. So this will be right hand. So from this, so this will be our right hand. So this will be right hand side, and our hydrogen will be left hand side. So there will be one chloride, and there will be one hydrogen is here like that. And if we show this side, so this side also like that. So our chloride. Like to similar to that molecule. So what happens? So in that molecule, there will be passing of sigma plane from this. So if that the case, there will be some. Um, so if I draw that molecule, like in that mirror image, so mirror image just exactly. So if we just intersection between these two, so this keep to the same molecule. So these are compound like meso compound. If a plus similar to that compound, so uh, these are not superimposable, but there will be some sigma plane passing from this direction. So these are similar to same half, is above and below. So these are example of meso compound. So this meso compound also not chiral. So this molecule our will be not chiral molecule, a chiral molecule. And for that next example one is when this molecule are all the chlorine in that above direction. So what will happen? So like that same. So if we draw like this one, like that. So for that cases, so there will be no sigma plane passing from here. So these are not our meso compound. So these are chiral compound. So this will be a chiral compound, and that next example, this one will be chiral compound. That's it. So I hope you understand that. Hello, so I am audible. Hello. So in this class we have to discuss to that problem. So I have summarized all of that from the past. So in these classes we are mainly just concentrated on the confirmation. So first the confirmation. So for any confirmation we have to write make that confirmation in that Newman projection. So this one will be our Newman projection. So of any molecule is given here. Like if I give some molecule like that. So we have to first make it in the Newman projection, and after drawing in Newman projection, then we have to tell which conformation is stable and which is the eclipsed conformation, which is staggered conformation, all of that. So mainly conformation are mainly that eclipsed conformation. Eclipsed conformation means when the angle between dihedral angle. What is the dihedral angle? Dihedral angle will be if this carbon, like this carbon, and there will be below one carbon, so these two carbon, and that the substituent place like this A and this D. So what are the angle between these two? So this will be our dihedral angle. If the dihedral angle will be minimum like 0, so then our conformation will be eclipsed conformation, and when the dihedral angle will be higher, above than 0, so then our conformation will be staggered conformation, like similar. So like this. Like if we saw in that example, there will be from the dihedral angle between this chlorine and hydrogen will be 60 degree, and between this chlorine and chlorine the dihedral angle is 180 degree. So after drawing that Newman projection, we have to tell which conformation is stable. uh, that eclipse conformation or staggered conformation. So, and also we have to draw that energy profile diagram. So for that, so like similar to these cases, the conformation where the 2-methyl group is the angle between this 2-methyl group, that is the diagonal angle, is 0 degree. So the diagonal angle is 0 degree, so this one will be our eclipse conformation. When diagonal angle will be 60 degree, this will be our Gaussian conformation. So when the diagonal angle will be 120 degree, this one also eclipse conformation, anti-clinical, and this when the diagonal angle will be 180 degree, so this one will be our anti-conformation. So after that we have to understand that why that which conformation is stable and which conformation not stable. So what are the things? So we have to know the steric. So the destabilization of any conformation is due to the one region is the steric region. Steric region means when the 2-methyl group at diagonal angle is 0 degree, this 2-methyl group is close to each other. So what will happen? So these two electron cloud are close to each other. So when those two electron means there will be repulsion. When these two electron cloud are in same position, so there will be repulsion. So then the molecule are not stable in that conformation. So they should try to that where the minimum energy, that is the most stable, that when that repulsion will be least one. So in that cases these two methyl groups far apart, so this one will be our most stable conformation according to steric. Then the torsion means that when that electron cloud of this bond and this bond, if these two bonds are in that same plane or same that diagonal angle is 0 between them, so then there will be repulsion between these two bonds, so this are also destabilized. And another is the destabilization factor is the angle. So if you go by sp2 or sp3, there will be some specific angle like 109 degree or anything. So if your angle is above that 109 or below that, so this will be not stable one. So like these three mainly destabilize our conformation. So after we draw that energy profile diagram, so that energy profile diagram, so this one will be 0 degree, two CH3 are behind to each other. So this will be least stable conformation because these are sterically crowding these two methyl. So when they are 60 degree apart, so this will be that stable one, like as compared to this. And when these two methyl are far apart, like 180 degree, when the rotation is 180 degree, so these will be our most stable conformation. So when there will be bulkier group and that bulkier group will be far apart from each other, so that will be more stable. And also here they discuss the what will be the destabilization factor, and how much energy will be lost for the destabilization. For that torsion between that hydrogen that will be around 4 kilojoule per mole, and that will be hydrogen and methyl, that will be 6 kilojoule per mole, and there will be methyl there like that, so that will be 11 kilojoule per mole. So another factor, what are the stabilizing factors? So they have tell that when the bulkier group, for bulkier group, that the anti-conformation is stable. But when there will be hydrogen bonding is present, so then that Gauge conformation, like this conformation, is stable. Why? When there will be hydrogen bonding happens when some electronegative group is present and there will be connected with one hydrogen. Like if we displaced this methyl like two OH group, like this two OH group, then what will happen? So there will be hydrogen bonding between this hydrogen and this oxygen. So if that will be the cases, the hydrogen bonding stabilize our molecule. So if that stabilize will happen, so for that cases there will be possibility of hydrogen bonding present in our molecule. So for that cases our Gaussian conformation will be more stable as compared to our anti-conformation. So for that cases this energy will be lowest one. So this energy will be as compared to that it will be little higher. So there will be chance of a hydrogen bonding, so then the Gaussian conformation will be more stable. And also there will be some electronegative element, like if we place some fluorine is here, or chlorine, bromide, anything is here, and there will be hydrogen, so then the chance of sigma to sigma star transition. So for that sigma to sigma star transition, so for that also our Gaussian conformation will be stable. So we have to, for sterically crowded group, the anti-conformation will be stable. If there will be possibility of hydrogen bonding, the Gaussian conformation will be stable, and if there will be only electronegative element is present in our molecule, then the Gaussian conformation will be stable. So then we have to draw that energy profile diagram. So in that energy profile diagram, so you have this some NH2 group and OH group. So this NH2 and OH group, so these are electronegative and there will be hydrogen present. So there will be possibility of hydrogen bonding between OH and NH2. So if there will be cases the OH and NH2 will be hydrogen bonding is possible. So in that cases our anti-knot, our Gaussian conformation will be stable. So we have to draw that energy profile diagram. Then we have to draw all the possible conformation. Then we have to tell. So Gaussian conformation is comes around 60-degree rotation. So this one will be 60. So 60-degree rotation is the most stable. So after 60, 120-degree eclipse conformation, then 180-degree will be our anti-conformation, like this anti-conformation. So as compared to anti, so this one will be stable one. Again another one. Similar analysis like eclipse conformation, then another Gaussian conformation comes around 300-degree rotation, and after 360-degree rotation, so this will be similar to that molecule. So our energy profile will be, diagram will be like that. When there will be Gauss is more stable and T1 is there less stable, then like this eclipsed conformation, then that another Gauss conformation, like that. So you have to draw all possible diagram of that molecule in Newman projection. Then we have to tell that Gauss conformation will be stable because this Gauss one, there will be hydrogen bonding is present. Then next example, in that chair and boat conformation, which conformation is stable, we have to tell. So like similar example I have given there, when there will be methyl group far apart like this, the bulk air group is far apart from each other, so this conformation will be stable. We also draw like this, when these two bromide groups far apart, like this conformation, so this conformation is more stable. And when this bromide is in equatorial position, so then there will be conformation will be like that. So we have to draw similar things like this, and we have to tell there will be that two bromide group are only 60-degree far apart, and there will be two bromide group are 180-degree far apart, and the bulkier group, if they are far apart from each other, so that conformation will be stable. So for this reason, the axial bromide is one with the stable conformation. Similar next example, like for tert-butyl when position in the axial and tert-butyl when position in the equatorial. What will happen when that there will be position in the axial? So in axial hydrogen also here it's here. So between these two axial hydrogens, so the tert-butyl group also the bulkier group. So there will be repulsion steric crowding between hydrogen and tert-butyl. So these conformations are not stable. And when they are in equatorial, so no such steric crowding uh, between this hydrogen and tert-butyl, because this hydrogen is above and this tert-butyl is below. So these are will be sterically crowding. So this one will be stable conformation. So between this axial tert-butyl and equatorial tert-butyl, the equatorial tert-butyl is will be more stable conformation. After that, we have to know that between chair and board conformation, which one is stable. So if we saw this conformation in that chair conformation, like I have draw, this one will be a board conformation and this one is chair conformation. If I draw this hydrogen, so there will be two hydrogen is here. So the steric crowding between these two hydrogen is higher. If anything is placed, the steric crowding is higher. So this conformation will be our least stable. So between chair and board, generally the chair conformation will be more stable as compared to board conformation. Then I have told some that chiral molecule and how when the chiral molecule was discovered, like around 1812. Chiral molecule means those molecules who are rotate are uh, plane polarized light. So if your rotation of positive and negative direction is similar rotation, so if we rotate if our molecule rotate our plane polarized light plus 10 degree, and that there another conformation like S conformation, if we rotate minus 10 degree, so overall net rotation will be 0. So for that cases, we have tell that molecule are enantiomer. Enantiomer means there will be presence of R and S isomer 50-50%. So this will be enantiomer. And when in that cases R and S isomer, like R and S isomer is someone is higher, like R is excess or S is excess. So that time we tell that molecule that time we call that enantiomeric excess one. So this chiralities comes in that point of carbon. So this one the point. So in that point of carbon, there will be four substituents are different. So for that reason, this chirality comes, and this chirality comes because in that CC bond, there will be bulkier group placed, and they are not in that same plane. So these are due to the axial chirality in the axis, and that chirality comes in the point. So these are we call point chirality, and in this cases we call the axial chirality. And this axial chirality in that molecule there will be presence of axial chirality. So for that molecule we told that that molecule was atrobisomer, and this atrobisomer was first discovered in 1922 by James Skinner and George Christie, and the properties of that molecule, how they behave, and chemical properties, and all of that things were discovered by 1933 by Richard Kuhn. So I have already told. So this one is our point chirality, and this one is our axial chirality. Axial chirality, like this is the bulkier group, and there will be bulkier group. So place of this bulkier group, these are not in that same plane. So and also this one and this one not superimposable to each other, so they are different isomer. So like atrobisomer, if we know that atrobisomer, so atrobisomer is mainly is coming the steric region. So it's steric. So mainly this comes from Greek word atrops. Atrops means without trans. So without trans means there will be steric region. So for the steric region, our simple CC bond rotation are not present. So the tran also not present. So for that molecule are called atrobisomer. So how that chiral molecule used as a drug? The chiral molecule maximum used as in drug application. So if we show this in that blue bar, so that blue bar one the single isomer. So between R or S isomer, that one will be single, like only R isomer or only S isomer used as drug application. And next I have told that one incident about that thalidomide disaster. So thalidomide disasters is the one is happened in 1952 after the Second World War in the Germany. So mainly this drug are used for um, uh, the pregnant women are mainly used for the morning sickness disease. So after that use of the drug, so they have born that disabled baby. So after that investigation was done, and what they tell that, so mainly this drug have content like this structure. So they are from R and S isomer. Between R and S isomer, the R isomer only are help to our disease, like to reduce our disease from the morning sickness, and that S isomer has the toxic effect. So the toxicity, so this toxic effect are help to uh, give this disabled baby. So, so we have to careful for every molecule. We have to first. So I have given this example for to we have to know that which molecule is chiral, and our molecule the chirality are stable or not, because this rotation of R to S isomer for some molecules happened in room temperature, and for some molecules happened some changing in environment, like if some is acidic condition and some in basic condition, by changing some pH, and that R isomer converted to S isomer. So if that will happen, and if we used as a drug application, so we have to be careful for that what isomer we have used, and if it is stable or not. So so we have to know that chiral molecule application as drug, and also the stability of that chiral molecule. So next we have to identify the molecule is chiral or not. So for these cases, what will happen? So we have to first give the some sigma plane is here. If they are similar half presents, if a plane sigma plane, if they are in similar half like this and this, are these are in same, so they are not chiral, so they are mainly meso compound. And if they are not superimposable mirror image like these cases, so they should be chiral molecule. Next example. So next example is like that. So if I give the plane, so they are not similar half, because this chloride is above, this chloride is down. So these are chiral molecule. So if I draw that mirror image of that molecule, so they are not superimposable to each other. So these are chiral molecule, and for next molecule, when in a single bond, there will be above chlorine and below carbon. And if we draw that one, draw that one like that. So for that case, what will happen? Uh, Cases, so there will be sigma plane passing to each other. So if that the cases, so like in that example, sigma plane is passing to each other. If that the cases, so this molecule are meso compound. So meso compound are not chiral. So this will be our achiral compound. So this will be our achiral compound. So we have to draw first. And in next example also, that two chloride are above, and if we draw like similar thing, if the two chloride is above like this conformation, so there will be no sigma plane passed between them. So these are chiral molecules. So this one will be our achiral molecule if we identify. So this one will be achiral, and the next one will be chiral molecule. So for these cases, if we draw like that, so our Cl will be, for one case Cl will be here, and for another case Cl will be here, and there will be methyl. I hope you understand what I am saying. So if you have any doubt or anything regarding these classes, or any any assignment you have not solved in your um, class assignment, like this assignment was that early assignment we have to solve, and that new assignment, if you have any problem you can contact me in my email id, this one given. So thank you to join, and if you have any question you can ask. Hello. So I think I am audible, no? Hello Bijoy. Hello. Hello. So I guess, do you understand? So Bijoy, where are you from? So if you have no more question, then I'll mm, complete today's problem solving classes. Thank you for joining.